All right, yeah, welcome back again. We are continuing in our course on statistics with how we are still looking at the parametric test. And the last time we looked at a single t-test. This time around, we want to look at a paired t-test, which is a dependent sample t-test. So this one requires one numerical and one paired, a paired group variable. So let's see how we're going to do it. By definition, a dependent sample paired t-test is used to compare the means of two related or dependent samples. Two related or dependent samples. And this is very important when we are trying to test uh, the same specimen or the same subject twice. Okay, it becomes dependent. For example, uh, we want to look at okay, uh, do vacations have impact on people's stress level? Just example. Okay, before the people go on vacation, we test their stress level or PB, right? So we allow them to go on vacation, the same set of people. So when they come back from vacation, we now test their PB again, we record it down. So we have two samples already now, okay? For the same set of people, take note, same set of subjects, same specimen, we record it twice. One before the effect of uh, 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 the vacation they went for, one after the vacation. Or for example, you can say, does the diet program have effect on the body weight of the people? Maybe they want to show if diet have effect on the people's weight. So what I think we have set of people, the same set of people, we measure their weight before the diet. We begin to administer the diet on them. Maybe after a period of time, we check the weight again. If the diet has effect on their weight, the same set of people, don't forget, we have two set of sample for them before the uh, diet, then after the diet. To always remember that when you're dealing with this kind of test, I mean paired test, it is always time dependent. There's always time involved, period of time involved. All right, there's always time before, after. There's time. Okay, there's maybe you want to check, you want to test something like a vaccine on a subject, for example, maybe on animal or maybe on mice. You gather maybe 10 or 20 mice, you inoculate them. You first test their status before and record it down before the inoculation to see if the uh to see how to see the result. Then you, after your inoculation, you inject them with cancer, for example, or with whatever disease you want to inject them. Then after some period of time, you administer something to them. You now check if there is any uh, effect of that particular vaccine on them after you have administered vaccine sometimes. So the same set of subject, okay, same set of specimen. We have a record before and record after. There are several examples on this. Several examples you can apply on this. Okay, several examples. So just understand the concept, how it works. It is time dependent. There is always period of time before, one after. Okay, so that is the concept of a dependent sample test. The same subject is tested twice. All right. Maybe you want to know the supplement, how supplements have effect on people or drugs. You test them before the drugs administration, and after the drug is administered, you test them again to see the effect. So the same set of people, nothing changes. So this is very important. So when you understand this concept, it is easy for you to apply the test anytime, any day, anytime you want it, because now you understand the concept, how it works. So there shouldn't be any confusion at all. Now, let's say we want to let's create an example data here to demonstrate this, where we use an example data set which contains the weight of 10 mice before and after pre-treatment. All right. So before treatment, let's say we have measured their weight right before treatment. Then after treatment, we want to measure their weight again and see if there's any effect. So let's say we have a variable called before, right? So we have let's curate a data set now. Let's run this line. Okay, let's say we have data set run like this, and we have after. Let's run the two together at the same time so that they no waste time. Okay, good. So we have run that. So we now say, okay, let's now combine together the two together now and create a data frame from it. So we create data frame for 10 of each. Don't forget the same specimen, the same subject, 10 is 10. So we measure the 10 before and 10 after. Take note of that. So we measure the weight of the 10 before and the weight of 10 after. So that's what we have done. So we want to know if there is any significant difference in the mean weight after treatment. That's all. So after the treatment, we want to know if there's any significant difference in the weight. All right. So let's create a box plot and first, and then check. You may also want to check the mean, maybe if there's necessary, if that required, be sure to check the mean for each group, right? If you want to, I think we can. Let me see if we can do that. We have a mind data. Let's see if you can pipe in this. Okay, mind data. We have mind data. Then we can see group by. Right. Let's pass in what is a let's go by. We have group here. Okay, group. Okay, we have group. Then we can pipe also. Right. Let's say we want to select. Let's summarize instead of select. Let's summarize. We want to find the mean. Let's say mean equals to mean open bracket mean of what of weight, right? Mean of weight. Want to find, can you find SD also? Let's find SD also. SD equals to SD of weight. All right. Okay, good. So we can stop it there. I think we have tried before we plot. Let's just see if this one work. I try to see. Open here, we close, we open, close. So we're supposed to close one more. 1, 2, 1, 2, 1. Okay, it's complete. Let's run this line and see what I'm talking about. If it work fine, good. So we are creating a group now. So this is before, this after. Okay, we have a mean. That's why I always keep this there, or always run this tidy fast. Okay, so just in case I want to use my piping. Okay, I won't have any issue. So that's why I keep it there. So you always run it and keep it there. So all the time. So I always like to keep my piping. So I will not be looking for it. Now we just finished running this now. Okay, where is it now? This is the we summarize here. So this is very important. Okay, so you should learn how to do this. Now we are group it now. These are grouping before and after. The mean is different. You can see that the mean is different here. Okay, and this is there. So this mean now before and after, is it significant? We have seen by okay, even by plot. Now let's plot. Let's say we plot now. What we are doing now, we have to pass our ggplot, our minds data set here, our aesthetic pass our. So what I do, I want to reorder here. Okay, this is ascending and descending issue. Okay, I want to reorder. I want by group. What that means that I want the normally when you plot now, I just S is supposed to be just weight alone. Okay, X is just as is just the rather the group. Okay, so or rather the weight. So now what I want to do, I want to rearrange it by group. So what I mean, so that it will be before then after. So that just say group after alone, then before later, because it will follow A B. So I want it to be BA. That's what I'm trying to do here. Right? Nothing special here. Okay, just for the order. All right. So if I run this plot now, okay, we have before and after. Normally it's supposed to be after before, but I have to do that so that you can have before and after. So you can see the weight here. You can see before and see after. See, they are not the same. You can see, me and looking at it now, they are not the same. The margin is from far, but you want to see if this particular difference we see is significant. So before you go further, you can check our assumptions. Okay, let's first check assumptions. Are the two sample paired? That is first question. Yes, since the data have been collected from measuring twice the weight of the sample, we measure twice. We measure before we administer treatment, then after treatment is administered, we now measure again. So we have them twice. So before and after. So that is the grouping. The same specimen, don't forget that. And number two, are the data from each of the two groups follow a normal distribution? So we can do this based on grouped data. So now we have two groups before and after. I can say group equals to before and minus weight equals to after. So we can do this and test. Okay, this method is different. So I know you are not familiar with this. If you are not, I will. So now we saw that our now looking at this now, our result show p value equal to 0.6141, which is which meets the condition for normality. All right, it shows that our normality assumption is met with Shapiro test. Okay, so in that case, the null of the null hypothesis of the normal distribution is not rejected. Okay, and so normality checks passed. So we now can proceed to the third assumptions. Number three, is it number three now? Suppose number three now. Yes, number three now. So number three, are the variance of the two samples equal? Now we have groups. Don't forget we have groups. So how do we do that? We use car library. So let's run car. We are going to use Levin test. So Levin test come along with car. So we run this. We pass in our mice data weight and groups. So this group data, we pass it here as usual. All right, so you can run this line of code. Don't mind the one, okay? This homogeneous of material, but this one can be taken care of as well, because this one is saying that it says 11 default my group co-factor. So we can just factor this guy. All right, let's factor this guy. So because group is a group factor, it's not factor at all. Because if you glimpse your data set, if you glimpse it, you saw that it's supposed to be a factor variable, minus $data. Okay, you can see that this one's supposed to be a factor variable, but its character supposed to be FCT, but it's not factors, and we didn't factor it in our code. So we have to factor it here, so that the error will be taken away. So now we have done that. We just apply factor here, so that so let's run again and see. You can see no more error. I mean, no more warning. It's not a warning, not error. So it does not stop our running process. So Levin test for objective interference center mean passed because it's not significant. Okay, so the null hypothesis of equal-variance is not rejected. P is 0.32, so we can continue with the test that assume equal-variance. So now that we see that we passed the 3 tests, and we can go ahead and perform our pair t-test. So nothing much different between the former one we did and this new one. The only difference that we are going to make it pair here. Okay, we say t-test, we pass our continuous variable weight here, our categorical data here, group, and we pass our data set here. Okay, then we now say pair equals to true. That's all. So when we run this line of code to give us the result, okay, that's the result we have now. Okay, we have this pair test. The alternative hypothesis true mean difference is not equal to 0. Yes, which is correct. Then you have 95% confidence interval, lower bound, upper bound. Sample estimate mean difference is 194. So our mean difference is 194. So we see that it's significant at p 0.00 and the rest of them. So we could report this as follows: mice before and after differ in the degree to which they are weighted, right? Which they are weighted. All right. Okay. We have this t is equal to 20.855 MP less than 0.01. Okay. The p-value of the test is this. I mean, this is 6.2 exponential minus 0.9, which is less than the significant level of alpha of 0.05. Our threshold. We can then reject null hypothesis and conclude that the average weight of the mice before treatment is significantly different from the average weight after treatment. Simple as that. So So you might want to test, you want to use the former before, and less or greater also is allowed. Okay, you can just add alternative equals to less or greater. So that is allowed also, you see. But this is what we just confirm now. So you can use your data set to perform the experiment, to test, to run the and see what you will get, and you can just conclude, and see how we continue the next class. Thank you so much for listening. I'll see you in the next class.